Hello, am I audible?
Yeah.
Okay, so let us start. Okay, I am Nanda. I am a coordinator in the CyberSecurity Club at C5, and today we are going to look at ASLR and how to exploit a binary even if ASLR were to be enabled using other means like format string vulnerability. Okay, so I will share my screen. Is my screen visible?
Yes.
Okay. So what is ASLR? ASLR stands for Address Space Layout Randomization, and what it does is it randomizes the memory addresses of shared library, the stack, as well as the heap. Um, this obviously makes it harder for you to exploit the binary because now the knowledge or the information about the memory address of certain shared libraries like libc that we saw in the previous session for using ret to libc will become difficult as we now no longer know the base pointer of libc. Okay, so why do we need ASLR? As I told before, uh, exploits like ret to libc require the attacker to know the base pointers of shared libraries beforehand. However, if we randomize this address so that every time we run the program it is different, then it will be difficult for the attacker to gain access to this memory address of the shared library and hence exploit the program. So how does it work? How ASLR works is it chooses a random base address for every shared library that your program is linked against, as well as it chooses a random memory address for the stack and heap as well. And it, those become the base pointers for the shared library or the stack. What that means is, suppose you have multiple variables on the stack, their relative positions are not changed. However, the relative position as in the offset from variable 1 to variable 2 suppose is 8 bytes, then that remains the same. However, suppose a variable 1 was at 0x f0 and variable 2 was at 0x f8. Now they might be at 0x a0 and 0x a8. So that is the base pointer for the stack is moved around. As you can see, this is an example of ASLR being applied on a program. Let us say the base pointer of the binary is 0x, whatever you can read the address over here. However, notice that between the two program processes, the base pointers for the heap, libc, and stack are all different. This is essentially what ASLR does. It changes the base pointer of shared libraries or the stack as well as the heap. So how are the other addresses randomized? As I told, relative addresses remain the same. So the address of the various functions within the shared library or variables or functions within the stack, the relative positions are fixed, and we can easily find out their address by simply adding their offset to the base pointer. As you can see over here, let us take the function system that we saw in the previous session to exploit the binary using ret to libc. Suppose system was at 9 bytes from the base point of libc. It will continue to be 9 bytes from the base point of libc even after ASLR. The only address that is changed is the absolute address. Say earlier it was at 0x7f this address plus 9. And suppose in the first run of the program. In the second run of the program, it could be changed to a different base pointer, but the offset remains the same. So as you can see, if we somehow figure out this base pointer, uh, If we somehow figure out this base pointer, then our job is done. We can employ the same tactic that we used earlier in red to libc that we saw in the previous session to exploit the binary. Um, okay, so if ASLR is enabled, you can see that when the program is run for the first time, these are the addresses of the variables on the stack. And when the program is run for the second time, you can see clearly that the addresses of the variables are changed. However, their offsets are constant. That is, address of A to address of B differs by 4 bytes, and that is the same over here as well. And address of C with address of B differs by 1 byte, and that is the same over here as well. So the only thing that has changed is the absolute position of the base point of the stack. However, the relative positions of the variables and functions within the stack remain constant. So, okay, so let us, they remain constant. So the only information now that we have to figure out is how to know the base point of the stack as well as other shared libraries in our program. So before we go into that, let's see how to, before we learn how to exploit the binary with ASLR, let us learn how to enable it. So, um, so in order to enable or disable ASLR, on Linux machines, it is stored at this virtual file, proc sys kernel randomized virtual address space. So in order to set it to, in order to enable ASLR, we have to write 2 into this virtual file. Now, why do we have to write 2? There are various different modes for ASLR to work with. 0 is ASLR, when ASLR is 0, it means it's disabled. Same as, okay, I think they are, I have to fix this right one. Okay, so when ASLR is 0, that means it is, when it is disabled, nothing is randomized, which is what we saw in the previous session. I had ASLR disabled over there so that the base pointer of libc does not change during subsequent runs of the program. If it is set to 1, that means shared libraries and stack and heap are randomized. And if it's set to 2, that means everything is randomized. So how do we do this? Let me zoom in on the terminal. As we saw in the previous slide, it is controlled through this virtual file on Linux machines, on Unix machines, on proxys kernel randomized virtual address space. So I simply have to, I can figure out what is it currently. Huh. So now I have enabled ASLR by simply writing out 2 into the into this virtual file. So how do we do that? We simply use this command. We echo 2 and pipe it into T to write it in. Anyways, uh, okay, that is shown in the slide as well. Okay, I forgot about that. Okay. So to know the current status, we can do, as you can see, since I've set it to 2, the current status of ASLR on my machine is 2, which is complete randomization. To disable ASLR, which is what I had done previously in the previous session, so that the base pointer to libc does not change, you simply write out 0, and now we can see that the status is set to 0. However, obviously, when we want to exploit a certain binary, they will have more protections enabled. That is, they will have ASLR enabled. So now we will take a look at how to exploit it with ASLR enabled. So I've gone ahead and enabled ASLR once again. Um, the command to enable ASLR is over here. you simply write out 2 to this virtual file. And to check the status, you can simply cat that virtual file and you can get to know whether the status of ASLR on your machine. Okay. ASLR is more effective in 64 bits than in a 64-bit system than in a 32-bit one. This is obvious because there are vastly greater number of memory addresses that could be taken in a 64-bit system. It is not exactly 2 per 64. Obviously, certain memory addresses are protected by the OS and not allowed for user memory, not allowed for user access. However, you can clearly understand that there's about uh, the orders of magnitude more memory addresses available for 64-bit system. This makes it much harder to brute force the base address um, if you do not know it. Okay, so I'll once again explain why we just need the base address. As you can see over here, the randomized address for any function or variable in a shared library or stack is simply an offset from the base address. So if we somehow know the base address, then then it is essentially the same as earlier. We can access any memory location we want since we know the base address, which is the only thing that is randomized. Okay. So how do we bypass ASLR? As we saw in this slide, we could either brute force it. However, this is not suitable, especially this is not viable since there are like 10 per 9 or 10 per 18 memory addresses that could be assigned to us. Instead, suppose there was a format string vulnerability or some other vulnerability through which we could leak the base address of the stack or libc, then this would make our life a lot easier. Yeah, so this in a brute force method, we simply guess the randomized address. We simply assume that suppose the base point of libc is this and the base point of stack is some other address, and we hope and pray that that is what it is. But the probability of that succeeding is extremely low, and this also wastes a lot of resources and will probably not complete within our lifetimes. So other better method is suppose the program had a another vulnerability through which we can find the addresses of variables like a format string vulnerability, then we can quite easily figure out the base pointer and go on with our exploit. So, okay, 1 second. I hope you all remember the previous in the previous session the C file, the vulnerable C file that we were looking at. I have just slightly modified it. Now it continues to read input until the buffer starts with quit. So I'll run it once to show you. So if I type whatever, it just gets repeated back. As you can see over here, we simply write into our buffer. And once again, you can notice that even though the buffer is only 64 bytes, we are reading in 640 bytes. This could be a programmer error who might have just added a zero. However, exactly these kinds of mistakes are the gateways for us to exploit the binary. So as you can see here, whatever I type is just echoed back. So it just reads into the buffer and prints it out. However, if I type quit, if I type in quit, it prints out quit and exits. You can see over here, this function simply compares two strings. And this argument, the stir n compare simply takes another argument, which is a number of bytes. In this case, I only want to compare the first 4 bytes. So if it's quit, um, it prints it out and then exits. Okay. So this is extremely similar to the previous um, in the to the program in the previous session. Now, however, notice that if I run it through, however, notice that if I simply use the exploit from the previous session. Um, this was exploit from the previous session where we simply I will make it where we simply figured out the address of libc using the LDD utility. As you can see over here, we cannot do that anymore because the address of libc keeps changing every single time. That is not fixed. So we can no longer say that the base pointer to libc is a static variable. We have to figure it out through a format string vulnerability or so. As you can see over here, we have control over the first argument to printf. Of course, helpfully our um, language server points out that it is up to the user to provide the format string, and it is potentially insecure. How is it insecure? You might have seen in your in the fifth session where you dealt with canaries that we can leak the canary through a format string vulnerability. In this case, we will try and leak the address to libc using a format string vulnerability. How do we do that? I'll simply run it through GDB. Okay, I've compiled it with output to a file called vulnerable. Now, okay, now we are inside GDB, and now we can see. Okay, let me run the file. You can see I can type in whatever I want and it echoes it out. Let me cut it. Uh, Now what we want to do is um, figure out an address that lies in between the start of libc and the end of libc. Why do we want to do that? Since as we have seen before over here, the offsets or functions or variables inside the shared library do not change. So if we somehow figure out an address of an variable or a function inside libc, then we can simply subtract the offset from that address. In this case, suppose the address of system that we leaked was a 0x whatever, and if we subtract 0x9, since that is constant, we already know the offset. Now we have gotten back the base pointer of libc. So I'll repeat once again. If we somehow figure out a memory address within the start and end of libc, then we are done, because now we can subtract that address from the start point of libc, and that is the offset. So if we know this offset, when we leak it once again in our program, we can subtract that memory address with the offset that we found, and we will find the base point of libc during the execution of the program. How do we do this? Um, we simply use a format string vulnerability. I'll just print out a bunch of pointers. As you can see over here, the second pointer 0x f7 f9 f5c0 lies within these two, because it starts at f7da and ends at f7fa. So this f7f9 memory address lies within libc, and we can use this to our advantage. So if I simply get the second address, this is the address that we want. Uh, so we will simply send the same payload that I sent over here. We'll find the second pointer from the stack. We will send it, and from here we will get a memory address of memory address of something that lies within libc. Now, if we know the offset of this memory address, so initially the known base pointer of libc is this 0xF7DAC000, as you can see over here, and the offset will simply be this address minus the base pointer. Now we have the offset of this variable. Now once we send this payload and get a memory address, if we subtract the offset from that memory address, we'll get the base pointer of libc for the particular program that is running, and the rest of our exploit remains the same. We will find the address of system, we will find the address of the shell string variable, we'll send a payload. This is slightly different to the payload that we sent earlier. I'm just appending quit. I'm just adding quit to the start so that it stops, it breaks out of the loop. And initially I was sending 76 characters. Since quit is 4 characters, I have to send 76 minus 4, 72 characters. Rest of it is the same. We simply add the address of system, some padding, and then address of the shell variable. This will um, call system with this argument, which will spawn a shell for us. Okay, let me exit. Okay. If you are unsure of how we got the system or the shell variable, I can show it once again. Um, we know that we can find out the libc that it linked with using the LDD utility. We know that it is located at this location. So now if I, and we know that this is an ELF file. So if I simply read this ELF file and grep for system, I will get the offset, which over here is, this is the offset 53390. This is in hex. So I simply add that offset to the base point of libc. How do we find out the shell? We simply use the strings utility and grep for the shell string that we want, which is found at this address, which is what I add over here. So that is how we figure out the address of system and the shell string variable. Once we have those two, we simply send the payload. Now we might wonder how we got 72 or 76. As I explained in the previous session, I'll show it once again. We can use the pattern utility in GDB. I'll just create a pattern of 128 bytes, store it. Then when I run the program, I'll paste this in. Now, as you can see over here, the buffer is only 64 bytes, and due to programmer errors, whoever wrote the program is reading in 640 bytes. So this obviously causes a buffer to overflow, and we'll get a seg fault. Okay, 1 second. I will go back to the previous version. Okay, so now we get a seg fault, and now we simply find the address of EBP and the offset of EBP, which is found at 72, and we want to overwrite EIP, which is at 76, which is at 4 bytes after EBP. So 72 plus 4, 76. So that is the offset that we want to write to. And that is how I got the 72 plus 4, 76. It's not a magic constant. We can figure it out using the pattern utility in GDB. Once we have that, we can spawn a shell. I'll show it running. Oh, oh, okay, I'll compare it. Yeah, okay. As you can see, I have a shell now, and I can Uh, um, I can use it however I see fit. Um, I will explain it once again if it was not clear before. It is extremely similar to the previous exploit. This entire part is almost the same. The only difference is now we do not know the base point of libc when the program is running. How do we figure that out? We figure it out using a format string vulnerability. We first leak a memory address that is inside libc. Then we subtract it from the base pointer of libc that we know to get an offset. So now when we uh, and now we have an offset of that particular memory location with respect to libc. So if we subtract the memory location that we got with this offset, we will get the memory address of libc while the program is running. I hope that is clear. So do you guys have any doubts? You can write it in the chat, or you can oh yeah, you can write it in the chat and I'll try to answer it. Okay, I guess there are no doubts. Okay. Mm, so that was it for the exploit. Now I will explain some intricacies of ASLR. Uh, okay, now you might notice when you disassemble a function using GDB, you might notice this at PLT. Um, so what exactly is PLT? To understand that, we need to know what is GOT, or Global Offset Table. So how ASLR works is um, through the use of this global offset table. This table is located at a particular fixed location in memory, and it's known to the linker, and it has the location to the absolute address of variables and functions. So how does it do this? It So whenever the program is run, initially the base pointers are all randomized, and the GOT stores these random base pointers, and from those, since the offsets of the functions or variables of the shared library or the stack remain constant, you can simply add the offsets and figure out the absolute location of the variables or functions in the stack or the shared library. So without GOT, or without the global offset table, that is with the ASLR disabled, we already know the absolute memory address of a particular variable, and we can simply find it out. However, when ASLR is enabled, we first have to traverse. We have to get the address of the global offset table, get the address of the GOT. Then we have to find out where the address of the variable is stored in GOT. Once we get that, we can simply read the address of the variable in GOT and get the value stored in that memory address. Okay, so what is the advantage of GOT? Um, it only needs to be constructed once initially at the start, and it is, however, it can be little bit slow because every time we have to go to the GOT, find out where the address of a particular variable is inside it, then go to that location and find the actual address of that variable. So in order to make this faster, we have something known as the PLT. So what is PLT? PLT is procedure link table. So what this does is, if during a program execution, if the function is being called for the very first time, it does this lookup in GOT. It finds out the address of GOT, finds the finds where this function finds where the address of this function is stored in GOT, goes to that location and finds the absolute address of the function. Now, this is what happens the first time, and this is known as a resolver. Once it has been resolved, that is, once the absolute location of this function or variable has been figured out, it stores it in order to make this lookup much faster. Instead of doing two indirections, that is, first going to GOT, then figuring out the address, then going to the absolute address, we can directly look it up inside PLT and get a faster lookup. So as you can see over here, the first time it is called, it goes into GOT, figures it out, and prepares the resolver. Once that is done, every time, for every subsequent invocation of this function, directly knows that can directly perform a lookup using PLT instead of going through GOT. As you can see over here on the first invocation, it jumps to GOT, finds out the address, and then stores it. In further invocations, is now in further invocations, we can have a faster lookup by using the PLT. Uh, as you can see over here, further invocations, we can directly access it using PLT. What is the advantage of doing this? We only need to resolve the functions when we use them, so we don't need to resolve every single function beforehand. And functions are relocatable using this PLT, that we can find the address even if the base pointers are randomized, since we know the offsets. So okay, this we have seen before, that is figuring out the base pointer. So that is basically it. There's another thing called there's another thing called PIC, Position Independent Code, or PIE, which you might have seen me pass in the previous session, or Position Independent Executable. What this does is it even randomizes the offsets. So if PIE is enabled, then this particular exploit of simply figuring out the base pointer will no longer work, because the offsets for individual variables or functions in that shared library or in the stack are also randomized. This offers an additional level of security, making it harder for us to exploit. However, this can also be um, bypassed using some other methods, which you can learn about by later sessions. Where is okay? This is how the kernel handles this this particular variable, the randomized virtual address space variable. It checks if it is if checks if it is set, and if it is set, it randomizes the base pointers of the shared libraries or the stack. Um, Anyways, this is the kernel code that does that. And that's about it. So if you have any doubts, I will explain it once again. If not, we can end the session.
If anyone has any doubt, raise their hands. Okay.
You can type your doubt in the chat. Uh, yeah, I can see no doubts in the chat. So I'll end the meeting. Thank you for attending.